We're going to discuss hydrogen orbitals in this lecture. It's section 11.7 through 11.8 in your textbook. So hydrogen orbitals we talked about yesterday in yesterday's lecture, and we talked about probability clouds. So the probability of finding an electron decreases as the distance from the nucleus increases, which we talked about yesterday. But the probability is never exactly zero, just like the buckshot analogy that we used. The edges of the orbital are not rounded and crisp, they are fuzzy, and electrons spend 90% of their time inside the orbital and 10% of the time elsewhere. So when we look at the hydrogen 1s orbital, the first level is designated as S. We notice on A, we see that fuzziness around there, how it's darker toward the center where the probability is higher, and this shows it as a sphere. All right, higher energy states are what happens when you excite electrons. So different types of orbitals are available for different energy states and different shapes of orbitals as well, and that's what we're going to get into next. Let's look and see how those energy levels are designated. So first of all, the first number that we're going to be looking at when we look at energy levels is called the quantum number. It'll be the first one. This is the principal energy level, and that means that there are discrete energy levels designated with whole numbers, and that also indicates the size of the orbital. So for example, it's 1, 2, 3, 4, 5, 6, 7. So there's a discrete energy levels, and number 1 is smaller than number 7. So the size of the orbital is also indicated. The second number we're going to look at designates the sublevels, and it actually is the shape of the orbital. So the second quantum number is going to be a letter. The letter is going to be such as S, P, D, F, depending on the shape of the orbital. I know this all seems confusing to start with. I promise that it will get that ironed out as we go along. The third quantum number describes the orbital's orientation about the X, Y, and Z axis. And the fourth one describes the spin of the electron. The first three quantum numbers must be used to define a given orbital, and no two orbitals have the same three quantum numbers. The fourth just describes the spin on the electron, so that can be the same. However, the first three won't. Those will always be different. This figure shows the first four principal energy levels in the hydrogen atom. So N equals 1, 2, 3, and 4, and the N equals 1 is the energy level closest to the nucleus. So here's our principal energy level. So here's the first, and which would be our first quantum number. So principal energy level 1, 2, 3, and 4. And within those are sublevels. Principal energy level 1 only has one sublevel. Principal energy level 2 has two sublevels, 3 has 3 sublevels, and 4 has 4 sublevels. Principal energy level 2, here's principal energy level 1 down here. So energy level 2 is divided into a 2s into 2p sublevels. 2s is the circular orbital that we're going to see, and p's are going to look like dumbbells. And these actually go around the x, the y, and the z axis. Like we said, principal energy level 1 is going to be smaller than principal energy level 2. And this actually, if you can imagine this, being inside of there, and then the nucleus in the center. So it's kind of like matryoshkas, as they have the shells one on top of the other, but are still orbitals, not orbits. This is what p orbitals look like in theory. So we draw them solid, but we know that they're probability clouds, where the center is the nucleus right here in the middle, and then we have the scattering, which is the possibility of where those electrons are located out here on the x-axis. We have a dumbbell on the y-axis and one also on the z-axis. So it's in 3 dimensions. So when you superimpose those, it looks like 3 dumbbells interlocking. So principal energy level 1 has electrons possible here in the 1s. Principal energy level 2 is here, and it has, this is 2s and this is 2p, and they're the same principal energy level, just different regions available, or probability-wise, where electrons are located or within those regions. And again, 3 is going to be, principal energy level 3 is going to be larger than 1, so it's 1, 2, and then 3, all the way up to 7. Here are the 3D orbitals. So we talked about the shapes. Let's go back and look. So S's are spherical. P's are dumbbells along the X, Y, and Z axis, and D's get really crazy. So they have, like on the Y-axis, we see 4 different probability areas, and then we see 4 more in this view, 4 more, and then look at the Z-axis, what it would look like. So you have to superimpose those on top of each other, and then imagine p orbitals, and then also surrounded by an s orbital in the 3 sublevels. So you can see why in the third principal energy level, why 3 would be so much larger than a 1 back at this picture, because this is going to have not only the 3 Ds, the 3 Ps, but also the 2 S's, the 2 P's, and the 1 S inside of it. The last thing we're going to cover today, and I know this is a lot of information, but the last thing we're going to cover today is Pauli's exclusion principle. And Pauli is not a parrot, has nothing to do with a parrot, like Pauli won a cracker. This is who Pauli is, and each orbital, he says, can hold 2 electrons, and the electrons repel each other. So in order to share the space, what has to happen is that the electrons must have opposite spins instead of the same spin. So one will spin clockwise and one will spin counterclockwise. So each orbital can hold 2 electrons, and the electrons must have an opposite spin, and that's called Pauli's exclusion principle. Let's go back and look at this. For example, this 1s can hold 2 electrons, this 2s can hold 2 electrons. In the 2p sublevel, the total number of electrons it can hold is 6. It can hold 2 here, 2 here, and 2 here. When we look at the D can handle 2 here, 2 here, 2 here, 2 here, and 2 here. So while there are 5 3D orbitals, each orbital can hold 2 electrons max, which makes the 3D able to hold a total of 10 electrons, 2, 4, 6, 8, 10 electrons. But each electron, there's 2 in this, and 2 in this, 2 in this, 2 in this, and 2 in this, they each are going to have opposite spins because of Pauli's exclusion principle, because those electrons are going to want to repel each other, so they spin opposite directions. Again, this will become clearer as we start to apply this information. Right now, you just have to have the information introduced to you.